Every time you flip a switch, charge your phone, or turn on a machine, you trust something you almost never think about. A thin electrical wire, quietly carrying power, hidden behind walls, inside devices, and beneath the ground. But here's the question: what if that wire is slightly too thin? What if its insulation has a microscopic flaw you can't see? What if, somewhere during manufacturing, something went wrong? That tiny mistake could mean overheating. It could mean insulation breakdown. It could mean a short circuit, a fire, or complete system failure years later. An electrical wire may look simple, but the reality is very different. Behind every reliable wire is a long, intense, and highly controlled manufacturing journey, one where precision is measured in microns. Temperatures are carefully balanced, and every step must be perfect. In this video, we're going deep inside that journey. From a raw copper rod, through drawing, stranding, annealing, insulation, and testing, to the final cable coil that safely powers the modern world. This is the hidden story of an electrical wire, and why every single step matters. An electrical wire may appear simple, ordinary, and almost invisible in daily life. Yet behind this modest appearance lies a complex and carefully controlled manufacturing journey. Before a wire can safely deliver electricity to homes, offices, factories, vehicles, and infrastructure systems, it must meet extremely strict requirements for dimensional accuracy, electrical performance, insulation integrity, and long-term reliability. In this video, we will follow an electrical wire from its very beginning as raw copper material, through each critical production stage, all the way to a finished cable coil ready for real-world use. Along the way, we will see why every single step matters, and how even the smallest imperfection can eventually lead to overheating, insulation failure, electrical leakage, or serious safety hazards. At its most basic level, an electrical wire consists of two essential components. The first is the conductor core, which is most commonly made of copper due to its excellent electrical conductivity, good mechanical strength, and high ductility. The second component is the insulation layer, which is typically made from materials such as PVC, polyethylene, or cross-linked polyethylene, depending on the intended application. The copper conductor is responsible for carrying electrical current from one point to another. Its properties directly determine how efficiently electricity flows, how much current the wire can safely carry without overheating, and how well the wire can tolerate bending, twisting, and vibration during installation and use. The insulation layer plays an equally critical role, even though it does not carry current itself. It electrically isolates the conductor, prevents short circuits, protects users from electric shock, and shields the copper from environmental factors such as moisture, heat, chemicals, and mechanical abrasion. In many applications, the insulation is the last line of defense between safe operation and catastrophic electrical failure. The manufacturing process begins with the raw material, a solid copper rod with a relatively large diameter, typically around 8 mm. At this size, the copper is far too thick and rigid to be used directly as an electrical conductor. So it must first be reduced to a much smaller and more precise diameter. This reduction is achieved through a process known as wire drawing. The basic principle of wire drawing is simple. The copper rod is pulled through a die with a smaller opening, forcing the metal to stretch and reducing its cross-sectional area. However, while the concept is straightforward, the execution requires extreme precision and control. The wire is never drawn to its final size in a single step. Instead, it passes through a sequence of drawing dies, each one slightly smaller than the previous. This gradual reduction is critical to prevent excessive stress inside the copper, which could lead to internal cracks, surface damage, or complete wire breakage. As the copper passes through each die, friction between the metal and the die wall becomes extremely high. Without proper lubrication and cooling, the wire would quickly overheat. Excessive heat can damage the copper surface, accelerate die wear, and create microscopic defects that may not be visible during production but can later compromise electrical performance. To control these risks, wire drawing machines are equipped with specialized lubrication systems and cooling mechanisms. These systems reduce friction, stabilize temperature, and ensure smooth, consistent wire surfaces. They also help extend the service life of the drawing dies, which must maintain extremely tight dimensional tolerances. At the end of the drawing process, the wire must meet strict quality criteria. The diameter must fall within very narrow tolerance limits. Ovality, which refers to the difference between the maximum and minimum diameter of the wire, must be kept to an absolute minimum. The surface must be clean, smooth, and completely free of scratches, dents, or cracks. Surface quality at this stage is especially important because any defect on the copper can later translate into a weakness in the insulation layer. A tiny scratch or groove may prevent plastic from fully covering the conductor, creating a thin spot where electrical breakdown can occur under high voltage. For many applications, especially those requiring flexibility, the conductor is not made from a single solid wire. Instead, multiple thin copper wires are twisted together in a process known as stranding. Stranding significantly improves flexibility and fatigue resistance. A stranded conductor can bend repeatedly without cracking, making it suitable for portable equipment, moving machinery, robotics, and applications where vibration is present. The number of strands, their individual diameters, and the twisting pattern are carefully selected to balance flexibility, electrical performance, and mechanical strength. After drawing and stranding, the copper undergoes a phenomenon known as work hardening. Work hardening occurs naturally when metal is plastically deformed, increasing its strength but reducing its ductility. While harder copper may be stronger, it is also more brittle and less suitable for bending and installation. To restore softness and flexibility, most manufacturers perform an annealing process. During annealing, the copper wire is heated to a controlled temperature and then cooled at a carefully regulated rate. This allows the internal crystal structure of the copper to rearrange and relax, restoring ductility while maintaining sufficient strength. Annealing not only improves mechanical properties, but also reduces internal stresses within the wire. This makes the conductor more stable during insulation and less prone to cracking during long-term use. At the same time, residual lubricants from the drawing process are removed, leaving a clean surface that promotes strong adhesion between the copper and the insulation material. Once the conductor is fully prepared, the manufacturing process moves to insulation extrusion, one of the most critical and visually impressive stages of wire production. Insulation materials are selected based on application requirements. PVC is widely used because it is cost-effective, easy to process, and suitable for many general-purpose electrical wires. Polyethylene and cross-linked polyethylene offer better electrical properties, higher temperature resistance, improved chemical stability, and longer service life, making them ideal for demanding industrial and power applications. Before extrusion begins, plastic pellets are typically dried to remove moisture. Moisture is a serious problem in insulation production. When wet pellets are heated during extrusion, trapped moisture can turn into steam, creating air bubbles, pinholes, or internal voids in the insulation layer. Inside the extruder, a rotating screw continuously feeds the plastic pellets forward through a heated barrel. As the material moves along the screw, it is compressed, mixed, and gradually melted into a uniform molten mass. Temperature, pressure, and screw speed are precisely controlled to ensure consistent material flow and uniform insulation quality. The copper conductor runs straight through the center of the extrusion die. As molten plastic is forced around it, a continuous insulation layer forms evenly around the conductor, creating a seamless protective coating. Two parameters are especially critical during this stage: insulation thickness and concentricity. Insulation thickness determines the wire's voltage rating and its resistance to mechanical damage. If the insulation is too thin, the wire may fail electrical safety tests. If it is too thick, material costs increase and flexibility is reduced. Concentricity refers to how evenly the insulation is distributed around the conductor. If the conductor is not perfectly centered in the die, one side of the insulation may be thinner than the other. That thinner side becomes a weak point, more vulnerable to abrasion, heat, and electrical stress. To achieve proper thickness and concentricity, manufacturers carefully control conductor alignment, die geometry, extrusion pressure, and line speed. Modern production lines often use real-time sensors and feedback systems to monitor these parameters continuously. As the insulated wire exits the extrusion die, the plastic is still hot and soft. To stabilize its shape, the wire immediately enters a cooling system, typically a water bath. Uniform cooling solidifies the insulation and locks in its final dimensions, preventing deformation or shrinkage. After cooling, the wire moves to the printing stage. Here, essential information such as wire type, conductor size, voltage rating, production standards, manufacturer identification, and batch numbers is printed directly onto the insulation surface. This information ensures traceability and compliance throughout the wire's entire service life. Next comes winding, where the wire is formed into coils or wound onto spools. Although this step may seem simple, it requires precise tension control. Excessive tension can stretch the conductor or deform the insulation, while insufficient tension can lead to loose winding and surface damage. Throughout the entire production process, continuous testing is performed to detect defects as early as possible. One of the most common online tests is the spark test. As the wire passes through high-voltage electrodes, any pinhole or abnormally thin insulation area immediately produces a spark, indicating a defect. When a defect is detected, the system can trigger alarms, mark the faulty section, or automatically stop the production line. This ensures that defective wire is removed before it reaches the customer. Offline quality control tests are equally important. Electrical resistance is measured over a standardized length of wire. Resistance values provide insight into copper purity, actual conductor cross-section, and the overall stability of the drawing and stranding processes. Another critical safety test is the high potential, or high-pot, test. In this test, a voltage significantly higher than the wire's normal operating level is applied to the insulation. The goal is to verify that the insulation can withstand extreme electrical stress without breakdown or leakage. Mechanical testing ensures that the wire can survive real-world conditions. These tests include insulation thickness measurement, concentricity checks, adhesion testing between copper and insulation, tensile strength tests, elongation tests, and repeated bending cycles. The purpose of these tests is not just to meet technical specifications, but to ensure long-term reliability. A wire must survive installation, vibration, temperature changes, and years of continuous operation without failure. Only after all quality checks are successfully completed is the wire approved for packaging. Each coil or spool is labeled with production dates, batch numbers, and traceability information, allowing any issue to be traced back to its source. And that is how a simple copper rod, through drawing, stranding, annealing, insulating, testing, and inspection, becomes a reliable electrical wire, quietly and safely delivering power in the modern world.